Okay, welcome back physics students to our next video where we're going to look at speed versus velocity. The equations for speed and velocity, not necessarily too complicated, just three variables, but I think understanding what speed and velocity means and how they're different in different scenarios, probably one of the harder things to understand in both Science 10 and Physics 20. So let's take a deeper look at understanding speed versus velocity. Okay, so to understand speed and velocity, we first have to be reminded of distance versus displacement. This was in a previous video, but just to remind you that distance is a scalar quantity, meaning that it has magnitude but doesn't worry about direction, just worries about the total route that you've traveled. Displacement is a vector quantity, and it does consider direction. It's worried about from where you start and where you end. So it's important to know those because all we have to do with those to get to speed and velocity is divide them by time. Okay, so speed going to be a scalar. It's our other scalar, distance divided by time. Where velocity is just going to be a vector. It's our displacement divided by time. And often pops up on the formula sheet like this for speed and velocity, d over t. Okay, so it kind of makes sense in the notes there and seems not too hard to write down, but let's take a look at what makes them different and what these formulas are actually representing. I suppose those ones up there. So let's take a look. So I'm going to use these two examples to show the difference between speed and velocity and what they mean. So on the side, we're going to have the yellow car. It's going to go 10 meters up, then another 10 meters up. The blue car, similar start. It's going to go 10 meters up, but then it's going to come 10 meters back down. Okay, so their motion kind of going to look like this. So I'm going in one direction, the blue one changing its direction. Let's start with the distance and displacement. Again, the distance, it goes 10 and 10, so 20 meters. The displacement, it ends up 20 meters from where it started, so 20 meters. We're taking direction into account with just forwards or positive. I don't necessarily need a north, east, south, or west. I'm going to say 20 meters forwards or plus 20 meters. You'll notice that those are the exact same numbers because we haven't changed direction. So then when I divide them by time, 20 over 10 is 2 meters per second, 20 over 10 is 2 meters per second, we get the exact same answers. Now I'm saying for velocity forwards and speed doesn't matter the direction, but our numbers are looking the exact same. So it kind of makes you think, why do we talk about speed versus velocities being different when we get the same answer? Well, the key for why they're the same answer in this case is, like I mentioned on this side, we're not changing our direction. We're going from here to here the entire time. The difference between these two quantities is if direction matters. If we're not changing direction, we should expect the values to be the exact same. So when we get the same answer, it's when we're going the same direction. Okay, so when we're going to try and see them as different is when we're going to change direction, and that's what the blue example's for. Okay, so looking up here, just to summarize, we were going 2 meters per second and 2 meters per second. Now let's look at the motion of the blue car here, forwards and back. Okay, the distance is actually the same because we go 10 meters and then 10 meters down, so our distance is going to be 20 meters. Our displacement, though, is where we start to see the difference. 10 meters up, 10 meters down, we end up in the same place that we started. Our displacement is 0. Okay. Once again, our distance and speed is going to look very similar because it happened in 10 seconds. Our speed being 2 meters per second, but our velocity giving the weird answer of 0 meters over 10 seconds is 0 meters per second. Kind of the reason why I made this video is how this confuses students. How the heck are we getting 0 when we know that the car is moving? What does the 0 mean? So what the 0 is actually talking about is it's telling us the average velocity. And that's the main thing to understand about what this is calculating. It's telling us the average velocity. So what does that mean? Well, it was going 2 meters per second here forward, same as this car was, but then it turned around and came the opposite direction. If I consider direction, it was going negative 2 meters. So 2 meters per second, negative 2 meters per second, the average there is 0. And that's the biggest thing to understand about these formulas. They calculate your averages, not necessarily what it's going at that moment. Okay? Does it work for speed too? Actually, it does. It tells us our average speed as well. because speed just doesn't care about direction. So if I get rid of direction here, what's the average between 2 and 2? Well, it's positive 2. My average speed would be 2 meters per second. So these equations, we call speed and velocity, are actually more appropriately termed average speed and average velocity. Let's take a look at another 2 examples to show how they tell us the averages. Okay, so this one I'm going to actually have going in the same direction. We're going to go 4 meters per second for 3 seconds. Each one's going to be a 3-second interval. Okay, so 4 meters per second, 9 meters per second, then 2 meters per second. It's going to look like this, and they're going to go a little bit faster, then they're going to go a little bit slower. Okay, so if I wanted to figure out the speed, I would need distance over time. We know the time here, so I said we're going to go for 3 seconds here, 3 seconds here, 3 seconds here. It's going to be 9 seconds, but I need to know how far we're going to go. Okay, well, if I take 4 meters per second for 3 seconds, that's going to go 12 meters, 4 times 3. 9 meters per second times 3 seconds, that's going to be 27 meters. And the last one, 2 meters per second for 3 seconds, 6 meters. Okay, so that's what the motion's going to look like. Add that all up, we're going to go 45 meters forwards, and again, 9 seconds, because 3, 3, and 3. So if I calculate my average speed, I go the distance, 45, divided by 9 seconds, my average was 5 meters per second. Notice in this example, I wasn't going 5 the whole time. It's telling me the average on that journey. If I calculate velocity, remember on the previous example, if you're going one direction, it should give the same answer because I end up 45 meters forward in 9 seconds, same answer. To show how this relates to averages, I'm going to take the average between 2, 9, and 4. I'm just going to add them all up and divide by 3. And look at that. It gives you 5 meters per second, which is the same, telling us that this is our average. For velocity, same thing. I get 5 meters per second. I should have a 0.0 here, but 5 meters per second for our average velocity. In my last example, we're going to change direction. Let's see if it calculates as averages in this case. So same scenario, 4 meters per second for 3 seconds, 9 meters per second for 3 seconds, but then we're going to turn around. We're going to go backwards for 4 meters per second for 3 seconds. So the car is going to go forwards, and it's going to go forwards faster, then it's going to go backwards at 4 meters per second. Okay, so again, I should look at my distances here. 4 meters per second for 3 seconds, 12. 9 meters per second for 3 seconds, 27. Negative 4 meters per second for 3 seconds. I'm going to come backwards 12 in this case. Okay, so my total distance, 12 plus 27 plus 12, that's the total route traveled, is going to be 51. I think it pops up here later, but remember that for the distance. But the displacement, when we're looking at here, if I go up 12, up 27, down 12, that's just going to be the 27 because the 12s kind of cancel out. We're 27 meters from where we started. Okay, let's see how this works for our speeds and velocity here. Oh yeah, 9 seconds as well. So our speed of 51 meters was the total distance. Divide by 9 seconds, 5.7 meters per second. Velocity, we went 27 meters from when we started, over 9 seconds, 3 meters per second. Okay, this is because we've changed direction. Reminder that these calculations are telling us an average. To take a look at how the averages are correct for this, let's look at speed first. If I take 4, 9, and a positive 4, because remember for speed, I don't care about direction. So I'm just taking the numbers, 4, 9, and 4, add them up and divide by 3, my average, 5.7. That's the average speed. If I look at my average velocity, where I do care about the negative, 4 plus 9 plus negative 4, that gives me the 4 and the 4 kind of cancel out, 9 over 3, and I get 3 meters per second, again matching this formula. So I'm hoping the main point of this video is to prove to you that these calculations are calculating your average speed and your average velocity, and probably should be on a formula sheet saying not just speed and velocity, should say average speed and average velocity, as that's what they calculate. So if I'm saying that, why then does it often say on a formula sheet that these equations are our uniform motion equations? Well, to look at that, I'm going to go back to that first example and black out all the other stuff and Look at this first one where the car is moving. This was our example of uniform motion. It was the only example all video where it's going the same speed and it's going the same direction. That's what uniform motion is. Same speed, same direction. In that case, if I wanted to calculate how fast it was going here, my calculations for speed and velocity gave me that number. Why does that work? I thought these were calculating averages. Well, I'm going at 2 meters per second the entire time. My average is 2 meters per second. My average and my constant speed are the same value. 2 meters per second, 2 meters per second, 2 meters per second the entire time. So that's why often we say to determine how fast you're going, use these equations when we're in uniform motion. So that's the only time they're going to give you the speed that it's actually going at every point. If it's speeding up, slowing down, changing directions, this is going to tell you the average values. I know that's a lot, but hopefully that helps you understand kind of what those formulas are. And I know it's blurred out here, but kind of why you get those weird answers for velocity. So just to sum up the video here, speed and velocity have these two equations. The speed is going to be used to find your average, not considering direction. The velocity used to find your average when you are considering direction. If you're in uniform motion, both of them work. They can both be used to calculate how fast you're going in uniform motion. So hopefully that title, and this is really kind of the simplicity of it, but hopefully the understanding of those makes a little bit more sense now. So thank you so much for watching this video. I hope it helped, and I'll see you in the next one.